Okay, kids, we're back. Whew. Have myself an orange and a banana. I'm a fruity guy. Fruity. Okay, let's get back to work. Now we know something about capacitors. What they are, they store charge, what they do. Okay, and then we know a little bit about how we get them charged. We got to connect them to a battery. That causes some flowage. Your negative and your positive actually on both sides have equal amounts of charge. But when we want to discharge a capacitor, we want to discharge it and get those electrons to move. So we're going to be looking at the electrons charge, the charge of those electrons. And let's see, we've got some equations now that go along with. You want to move something within an electric field, okay, maybe within a capacitor. You got to move it from part A to part B. You might have to do some work because it doesn't want to go there. And if you let it go, it does some work on the way down and converts into kinetic energy. So we have these equations that we can use. And let's dive into a capacitor and do some math with the capacitor. Oh, I hate math. It's physics, people. It's physics. What did you think was going to happen? Okay, so let's look at a capacitor and do some math with capacitance. Capacitance, what's that? Okay, so capacitance is defined as the amount of charge per volt being applied to the capacitor. What do you mean? Well, take a look at this thing here. Again, my big fat Larry here. This is the 1 farad capacitor. And this one, I believe, was a 60 microfarad capacitor. I could run back and grab one of these, but I think I'm right. I think it's 60. So why is there a difference? 60 microfarads versus 1 farad. Okay, what's the difference between them? Well, look at them. One's a lot bigger than the other one. So check this one out. Imagine unraveling this thing and taking all the metal out of that and comparing it to this. There's a lot more metal here. More metal means you can store more electrons. Electrons are stored in the metal. So you have more metal, more electrons stored. Therefore, more electrons stored per volt. Now, voltage means that we have to connect it to something. So you have to connect it to a battery or a power source, or even a wall outlet, 120 volts, or maybe a 3-volt battery, a 6-volt battery, a 9-volt battery, 12-volt battery, whatever. You connect it to a power source that gives it a little bit of push. That's voltage, is our power source. And we charge up, we give charge to the capacitor when we connect it to a volt source. And now we get a capacitance, which refers to how many electrons we get stored. All right, so now, and don't confuse this. This can be confusing. The unit for charge is the coulomb, remember? Coulomb, and that's a C. And that C is different than this C. And C is for cookie, that's good enough for me. However, in this case, we've got to keep the C's correct. This C is for capacitance. This C that I use here is for coulombs, and that can get confusing, and you'll probably make a mistake with that along the line, but just be aware of that. We'd be careful when we're doing calculations. Are we looking at the C for coulombs, for charge, it's Q, or are we looking for C as for the capacitance of a capacitor? All right, let's see. Now, if we look at the units here, Q is C, right? Oh, confusing. It's coulombs, and volts, if we look at our volts is ED, and that's electric field strength, so that's newtons per coulomb. And distance is meters, and a newton meter, a unit analysis for you kids, is a joule. So this is joules per coulomb, which we should know at this point, or maybe you kind of knew it at one point, like maybe a few days ago, but now you forgot it, that a volt is the amount of joules per coulomb, remember? Not just total joules, but joules per coulomb. All right, so that's what we got here. And if I were to take this and multiply by the reciprocal, okay, I get coulombs squared. All right, coulombs squared. And so that would be coulomb squared per joule would be my units. And that's actually, this whole thing here is given a special name. So we don't have to, I'm going through unit analysis here, but you don't have to memorize this. Just know that capacitance is measured when we have coulombs per volt, which again comes out to be coulomb squared per joule, is a farad. That's called a farad. So this whole thing just ends up being an F. And what you need to know about that is the higher the farads, the more storage capacity of your capacitor. Okay, all right, let's move on. Now you can see up here, we're going to very soon get into this. This is called the, this is our permittivity, I can't speak, I'm so excited. Permittivity of free space, it's a constant that's given. It's on the AP sheet, you don't have to memorize it. But you can see they've got some funky units up here. And so we'll get back into this. So this is funky units. This has to do with a capacitor, and we'll now move into this. Okay, so now our capacitor, go back to our original equation here. Capacitor is the amount of charge per volt. Of course, I can move this around and I can find voltage of a system if I divide it by the charge per capacitance and vice versa. And we'll come back to that. We're going to have to do that in some of our equations that follow. But let's look at another capacitance equation. You will find this on the AP sheet, that one as well. You'll find this next one on the AP sheet. And let's go through. What is this one? This one says a capacitor, or capacitance is equal to K times E sub naught. Oh, that's that. That's our, it's called, the permittivity of free space, the capacitor constant. We're going to use that for a capacitor constant. And let's see. Well, let me ask you. You do. Let's see. If we're going to try to calculate capacitance of a capacitor based upon the physicalness of the capacitor, then what would we include? Well, this is 1 farad, this is 60 microfarads. This one has a lot more metal in it than this does, so that must have something to do with it. Okay, it must have something to do with more metal. So we have to put in our equation to figure out the capacitance of a capacitor, how much metal there is. Now we don't do that by mass, we do that by area. There's surface area here, there's surface area here that we can hold electrons on. So the more surface area I have, the more capacitance I will have. So that's a direct relationship. So we'll put A, area of the capacitor, okay, the area of the metal that we have available to store charge, is directly related to the capacitance. Also, how far apart the two sheets of metal are. That makes a difference. The farther apart they are, or the closer together the metal is. So let's say we've got two sheets of metal, one sheet here, they're really close to each other. And maybe we have one sheet here and one sheet here that are much farther away. Does that have something to do with the capacitance? Heck yeah, it does. Well, one, it's in the equation, so yeah, I'm talking about it, so yeah. So it does. And in fact, if you look at this, there's an inverse relationship here. So the greater the distance, if I put a greater number in here, okay, in the denominator, I'm going to get a lower number here in the capacitor. Okay, so let's check that out. See why. This is kind of interesting. It's kind of fun. This is going to be brain time. Turn on your brains, kids. Turn them on, because this one's going to take some brainage. So let's say that I've got a capacitor here and here. And here's the positive on top, negative on the bottom. All right, I've got a whole bunch of electrons stored here. I've got some electrons stored here. And I have a greater distance here than here. Which one would have the higher capacitance? Well, you know that the larger the distance here, the smaller the capacitance. So this one's going to have a smaller capacitance. So we'll go arrow down capacitance compared to this one. This one will have a higher capacitance. Well, why is that? Because if the electrons are really close to the protons, which they want to get to, they like each other. If the electrons are very close to these, they want to get there, and it's going to be difficult to separate them. It's going to be difficult to keep these things separated. So what ends up happening is the negatives here being very close to the positives here can help drive the electrons out. The electrons that are remaining here. Now, of course, I put 4 positives. Doesn't mean there aren't any electrons in here. I mean, come on, let's not be crazy. We didn't get rid of all the negatives. We just got rid of some of them. But there's still negatives in there. So when we can get rid of all those negatives, you're not going to get rid of all the electrons around the nucleus. You're just not going to do it. Okay? You try. Yeah, there you won't. Yeah. So you can't. But we can still put, if we get this negative plate close to this positive plate, that pushes out more electrons from this plate because they're, of course, repelled. And what does that do? That drives more electrons around to be stored on this plate. So the closer we can get these two plates together without them discharging, because we don't want them to discharge, kind of like so you're on the fence here. Oh, I want them to get far close together, but I don't want them to discharge. Balancing act, people. Balancing act. And so if we can get this close without it discharging, we can cause a higher capacitance. We can drive more electrons out, more electrons in, and therefore that'll increase our capacitance. All right, which is also why you see that these capacitors, I mean, these pieces of metal are really close together. Like so close you can't even see them. Like, oh, I can't even see them. You're so close together. Yeah, they're really close. And that drives your capacitance up. So if you have a smaller distance in here, increase your capacitance, your ability to store charge. All right, so it helps aid the driving of electrons out of one plate and then onto the other. All right, okay, that's like, yeah, okay. All right, so that increases our capacitance. So distance has something to do with it. Now, of course, I just erased the two things, so I want to refer back. I do that all the time. I erase a thing, and I go, wait a minute, and I go, oh, crap. So here we have our plate and plate. In between here, we have our dielectric. That's our insulator. That's to help maintain or help keep these electrons separate from this plate. Because if they touch, they're going to immediately discharge. They're going to shoot over to here. These are negatives. They want to be here, so boom, so keep them separate. Don't let them do that. And your dielectric that's the job of that dielectric, making sure that those electrons don't jump until you're ready to have them jump. So your insulator is going to be important. If you have a much more strong insulator, well, then you can keep those things from jumping and get the plates even closer before they'll discharge through. So that K here has to do with the dielectric. And this value is called your dielectric constant, depending on what you have. Do you have glass? Do you have plastic? Do you have dry air? Do you have whatever your insulator is? So that's going to have an effect on it. It's a multiplier. So the better the dielectric, the better the insulator, the greater your capacitance. The more electrons you can get stored on there before they would make that jump. And in the notes, I listed some different dielectric values. Dry air is given a dielectric of 1. And off the top of my head, I can't remember some of the other ones. But you have dielectric values for different insulators. Now, this here is a constant. It's called the permittivity of free space constant, and it's this value, and it goes into the equation all the time. It's permittivity of free space, so like space, the final frontier kind of a thing. And this multiplies by this value whatever that dielectric is. If the dielectric is wax paper, maybe it gets a 2. If it's glass, it gets a 5 or somewhere around there. If it's dry air, it gets a 1. But that's going to affect your capacitance. Okay, so this video's getting long. I didn't want it to be that long, but I have another video to make. Okay, so what do we know? Now we know there are two equations that deal with capacitance, and they both have to do with how much charge you can store. And that has to do with several factors. One, the physical characteristics of the capacitor, okay, how much metal and how far the plates are, and what is the insulator in between. Those are the factors that will determine how much charge you can get stored. Okay, this capacitor equation here tells you about charge you can store, and also has to do with the amount of voltage that the battery is providing. So you cannot get a capacitor to be have more potential between the two plates, potential means voltage, than the battery that's charging it. So you have a 3-volt battery charging your capacitor's potential difference between the plates can only be 3 volts. It can't be more than that. All right, you with me? All right, so I'll stop this video because we're almost approaching 15 minutes, and I have another video to do. I know so many of them. I'm so sorry. This is my sorry face.